number 61.3 from Sardar Patel Institute of Technology, Mumbai, decided to develop a voice-operated smart wheelchair with patient monitoring system under the mentorship of Dr. Surendra Singh Rathod for the Texas Instruments India Analog Design Contest 2012-13. It is a novel wheelchair which consists of two modes of operation. The first one is control using voice commands and the second one is control using an accelerometer, which is a rather unique feature of our project. It also consists of a patient monitoring system which measures the body temperature and the pulse rate of the patient. It sends an SMS in case of emergency to the doctor using the GSM module interface. The main reason for choosing voice recognition was that it is not only a simplest and the natural mode of communication, but we thought that it might prove to be very powerful tool for the differently abled people to automate their motion. Now let us get familiarized with the hardware used. We have used the C6713 digital signal processing kit provided by Texas Instruments and manufactured by Spectrum Digital. The microphone input is given to the mic in port of the C6713 DSK. We have used an isolated word small dictionary consisting of control commands left, right, back and forward to maneuver the wheelchair. The voice recognition algorithm used is the Mel frequency cepstral coefficient algorithm. To drive the motors of the wheelchair, we have used an edge bridge circuit which is controlled via the ATmega16 microcontroller unit, which is designed by us. The motors used in the wheelchair are 12 volt 100 rpm geared Johnson motors suitable to bear a torque of up to 10 kg centimeter. When the speech command is recognized, sine wave of a particular frequency is generated at the line out of the C6713 DSK. This sine wave is then fed to the analog to digital converter of the ATmega16 microcontroller. For example, when right command is spoken, a sine wave of 12 kHz is generated at the line out of the C6713 DSK and fed to the ADC. Depending on the digital value obtained, the enable signal is generated by the microcontroller and given to the motor driving circuit, which in turn drives the motor in the appropriate direction. Now let us see the demo of the wheelchair control using a voice operation.
Right, back, left, forward,
The second mode of operation is controlling the wheelchair using an accelerometer. The main reason for interfacing an accelerometer is that the voice recognition system may fail in noisy environments like malls, railway stations, public places like gardens, etc. Then interfacing an accelerometer will provide an added alternative to the patient for maneuvering his wheelchair. The acceleration sensor used is MMA7660 digital acceleration sensor provided by Freescale Semiconductors. It uses I2C protocol to communicate with the microcontroller. The accelerometer is interfaced with ATmega16 microcontroller. Depending on the orientation of the accelerometer, different values are generated in its tilt register. Based on these values, we have programmed the MUSI to drive the motors. To move the wheelchair in the forward direction, you move your hand forward. Now to take a left turn, you tilt your hand in the left direction. To take a right turn, you tilt your hand in the right direction. To move backwards, you tilt your hand towards yourself. In order to stop the wheelchair, you just tilt your hand upside down and the wheelchair stops. This was the demo for the wheelchair controlled using an accelerometer. The patient monitoring system is interfaced with ATmega16 microcontroller along with the GSM module. We have used LM35 temperature sensor from Texas Instruments. It is a precision centigrade temperature sensor which has a resolution of 10 millivolts per degree Celsius. The communication between the microcontroller and the GSM module is achieved via MAX232 IC from Texas Instruments and DB9 serial connector. The pulse rate sensor consists of IR LED photodiode pair to sense the heartbeat, a two-stage amplifier and LED LDR pair for output purpose. Now we'll see the demo of the patient monitoring system. The LM35 temperature sensor is connected to port A0 of ATmega16 microcontroller. The LCD connected displays the instruction to be followed by the patient for measuring the temperature. In order to get accurate reading, 20 samples are taken from the ADC channel and the average of these samples is the measured temperature of the patient. The temperature calculated will be measured on the LCD screen. It is 94.03 Fahrenheit. For pulse rate measurement, the fingertip is placed on the IR photodiode pair. The voltage across the photodiode increases as a heartbeat is sensed. The change in voltage is then amplified using MCP602 op-amp to give high output via the LED. This output is connected to port A1 of the ATmega16 microcontroller. To demonstrate the working of GSM module, an SMS is sent on purpose indicating the patient temperature and the heart rate. It was a great journey and a learning curve for our team. We have worked really hard on our project, but we know that there is a scope of improvement and we hope to better our own design. We believe that this project of ours will be beneficial to the society. It was a large project and there are quite a few people who have helped us. We would like to sincerely thank them, starting with our mentor Dr. Surendra Singh Rathod for his constant encouragement and support, Professor K.T. Talele for his valuable insight on the DSP, and Professor Manish Parmar for his immense help in understanding the microcontrollers. We would also like to thank all our classmates for their constant support and help. Special mention to Kapil Majumdar for his help in designing the mechanical prototype of the wheelchair. A note of thanks to Ronak Choksi, Rohan Daftari, Shimoni Shah, Kartik Haria for their constant support and motivation.